Hello, I'm Stan. It's going to be a short lecture on what Dr. Rathel talked about last week, and that's peer review. And you hear that in the news all the time. What is peer review? This is peer review data, especially with the pandemic. You've been hearing it a lot in the media. Peer review is how science works. But my suspicion after over 30 years of teaching in the university, college, is that you guys probably really don't know what peer review is. So I'm going to give you an example. As a former researcher for 25 years, I've been peer reviewed a lot. It's kind of a painful process, but it's how science works. And essentially what peer review is I try and send my results that I want to get published, which is how scientists communicate with each other. I have to go through 3 reviewers. And essentially those reviewers can call me out. This isn't the way it does. Shouldn't work. You used improper statistics. We don't like your methods. Essentially they get the right to call BS. And that's not the way things always work. If I go to a couple websites, here is the Safari Club website. You have a young lady there that's with a rifle. Obviously she has a hunting TV show. And if you went through that website, you would see pro hunting, pro hunting, pro hunting, pro hunting. If I was to go to the Humane Society, you would see nasty hunting, nasty hunting, nasty hunting, nasty hunting, nasty hunting. No one reviews those websites. I have websites, I've had websites, I can write anything I want. I could start a website and say the reason the Japanese bombed Pearl Harbor is there was too many chefs and they needed more work. There's no one who would challenge that. There's no one who would, no, you're not putting that on the web. And that's how science works, because we control each other. We submit to a manuscript, to a publication, and I like that mountain lion kicking picture. And then we're told we go through a process, and we may get to publish, and we may not. Okay, by the way, I have my quote here. I hope I look professorial for you. I have a nice sports coat on. And since it's hot, I'm going to take the damn thing off. And you're going to find that I'm a kind of an informal person. So this is really me, with a ball cap and my glasses there so I can read. Anyway, I just want to show you an example. I did a lot of research on bears, and I'm going to show you an example of what it took to get this paper published. This is a journal article. It was in the Wildlife Society Bulletin, The Effects of Wildfire on Black Bear Demographics in Central Arizona, by Stan Cunningham and Warren B. Ballard, who was my co-author. And this is based on a study that I did. I'll give you some, whoa, hang with me here. My mouse doesn't want to seem to work. Hang with me. I can't see here. There we go. On the effects of wildfire on black bear demographics on a central Arizona sky island. So, in 96, where were you? In 96, I was studying several carnivore species. I had developed a survey system for mountain lions. So Game and Fish said, well, we need you to develop surveys for bobcats, coyotes, bears, several other species, anything with sharp teeth. They wanted me to try and develop a survey. We first started using those remote cameras. And in April of 1996, my whole study area burned up. So all my cameras, all the work I'd been doing, lost. Very much like just happened this summer. And at that time, it was the second largest fire in Arizona history. Burned approximately 135 square kilometers and destroyed 90% of the vegetation on Four Peaks. If you don't know where Four Peaks is, it's approximately 50 airline miles east of Mesa. I can see it from my house. My suspicion is on a clear day, which we're not going to get because of the wildfires in California, you can see Four Peaks often. And believe it or not, it has one of the highest black bear densities in the entire United States. There's a place in Alaska that has density. There's a lot of bears in Arizona, whether you knew it or not. So after the fire, there had been a study up there that determined that that was the highest density of black bears. So the powers that be, Game and Fish, that everybody has a boss, said, well, what do you think it did to the black bears? And so it's an interesting question because ecologically fires can be good. Now we're going to get into that later in the semester. I don't want to have a lecture on that now. But fires are a natural part of the system. And fires in Arizona, we used to have fires in our forest in Arizona every 2 to 10 years, which is a lot different than we do today. And it was because we have such a hot forest summer, May and June. And then in July, the lightning comes. And believe it or not, the Mogollon Rim has the second highest number of lightning strikes as any place in North America. Key West has some more. And those lightning would strike dried up vegetation, and it would start a fire. Now, these were quite bit different fires than we have today because there wasn't as much fuel. Because it burned so often, there wasn't a lot of dead trees. There weren't any dead trees. There wasn't a lot of whole twigs, dead grass on the ground. And the fire would burn 5,000-6,000 acres and burn itself out. And then 2 to 4 years, 6 years later, it would do the same thing again. So that's what Arizona animals evolved with. Today, the fire industry intervals are greater than 40 years. We have, those of you who've been up on the rim, you can see very dense forest like this. 400 times the number of trees that we used to have. And I'll go into how they all determine this later in the semester. And so it was interesting, you know, we essentially have ecologically different fires than we used to. That interval is caused by humans. We have less fires now, not just because we put them out, but actually had a lot to do with cattle grazing in the late 1800s and early 1900s. But this is what our fires used to look like here in Arizona. This is what our forest looked like more in Arizona. This is what they look like today. And so it's quite a bit different. And so I went through the literature that somebody else had published through that peer review process. And I determined that, hey, looks like fires can be good for bears. It starts berry growth, gets shrub going again. This may be great for Arizona bears. But we didn't know. So that fall, I spent quite a bit of time hanging bait, which means dead carp, anything that smelled good. And we didn't find any bears. They never came and visited our sites. And I'm pretty good at tracking, and I would lay it out so that I could see a bear if it came into the area, and they weren't there. We rode horses a lot, rode ridge tops, wash bottoms, didn't see any tracks, didn't see any poop. So I didn't know if this fire was good or bad for bears. But not seeing anything, it didn't look like it, so we decided to start a study. We looked at the age and sex ratios, the reproduction, the survival, the density, and movements. And we compared those to a study that had been done 15 years before in the exact same area that burned. So we have some similarities there. We have data on what it looks like for a non-burned population, a population of bears living in the area before it burned. And so now we're going to look at it after it burned. And we're also going to look at it next door. This particular mountain burned this summer. But at that time it was unburned. So we studied bears here. We studied bears. This red outline is the fire boundary. Inside that fire boundary. So we were capturing bears, putting radio collars on them, taking information, weighing them. In the winters we would crawl into the dens to see how many cubs they have. Yes, I've actually done that over 30 times. It's pretty exciting. You know where your heart is. Within this red area were what I call unburned islands of vegetation. So fire is not complete. It doesn't burn everything that's alive. And one area was 3 square miles of forest, basically left. And I used to call that area 3 Mile Island because it was an island of vegetation within a charred area. And we went to work. So we wanted to compare bear populations there versus the unburned area. And a lot of people have questions about bears. Do bears, what in the woods? And so we made this discovery. I have photographic evidence to prove it. Okay, I'm going to go through this real quick because this isn't a fire ecology or a bear. This is more on peer reviewed. I want to get back to what I'm saying. So we looked at the number of our study areas, and this is some of the data slides. And the guy who studied them before found 1 bear per 3.4 square kilometers, which is about 1 bear per square mile. That's a lot of bears. However, if I looked at the unburned areas within that burn, there were 4 bears per square mile. That's an extremely high density. When I went next door, 1 bear per square mile, not 4. We found by capturing bears in the area that the number of males was much higher. Essentially, we caught 4 different males for every 1 female we caught. When the study was done before the fire, there was 1 male per female. Next door, there might have been almost 2 males per female. Males are easier to capture. It's hard to make sure. And these were big males. These guys were huge, and they were covering a lot of territory. And they were basically moving from all these unburned islands within the burn. It's hard to be black or dark brown in the Arizona sun in the summertime, so they needed vegetation, needed the shade to stay cool. And of course, that's what the only food is for them. As I said, we went into the dens to determine number of young. That is mom with an ear tag, and there is at least 1 of her cubs right there. And I have a syringe on the end of that stick, and I am going to crawl in, and I am going to poke her. They call it a jab stick, but I would gently poke it in, just to make sure that she didn't get too upset or too excited about what I was doing. And we'd breed the cubs out, we would sex them, weigh them, make sure they're okay. And on the nearby mountain, there were 13 cubs produced over that 4-year period, and 5 females. They had cubs every year. So every time you have 2 to 3 cubs in the den, and every time I went in, and they were there. However, and this is sad, none of those cubs survived. None of them. So in the area where it burned, those cubs they didn't make it. Why? They were eaten by male bears. And this is a long story. I don't want to go too much into bear biology, but male bears will kill the cubs of a female. If he hangs with her for 36 hours, she quits nursing. There's no more lactation. She will come back into estrus, and he can breed her. So it's a very weird sort of foreplay. And so given there was 4 males per female, extremely high density, it was almost impossible. It wasn't possible for those cubs to survive. And next door, though, it was just like normal. 36%, 48% survived in the study that was done before. So the high densities, the amount of food available at least was good enough, so the females were in good enough shape that they could produce cubs. If they're not in good shape, they don't have young. It's a long story, but they won't. We would catch them in May and June. We would weigh them. I would go in the den, and they were 100 pounds heavier, which is pretty common for bears. They gain a lot of weight over the summer. So it was kind of like, who are you? You were little when I caught you, and now you're huge. So there was plenty of food. So here in this presentation that I gave to other scientists, the cub mortality was induced to the increased number of males. And the gentleman who studied them before documented females avoided males by using areas of higher elevation and steeper slopes. The higher elevation, the steeper slopes were there, but there weren't any big trees. There wasn't any vegetation, so they couldn't go there. So they couldn't afford the males, which is what they would prefer to do. There's a summary slide. Normally I would take 25 minutes to do this, but the black bear population was negatively affected by the wildfire. It was not good for them. Other studies have found that fire can be good for bears. This one wasn't. There wasn't any cub survival in 3 years of monitoring. And I'm still concerned about the lack of ponderosa pine. It's just not coming back. So that area has completely changed because of that fire, which was abnormal because it wasn't, we have 400% more trees, so it was much hotter. We lost our ponderosa pine forest in that area. There's only a little bit left, and it doesn't look like it's going to come back, not with global warming. Okay, so to do a study does no good unless you publish it. It kind of gets lost in your file cabinet, and anybody who wants to do good things for bears, if they can't read it, you're not helping anybody. So, and publishing is how science moves forward. And we disagree a lot and argue a lot. And a lot of that has been made public now here with the pandemic. WHO says this, CDC says this, the American Medical Association said this. I think the public is kind of surprised by that. I'm not. Anyway, back to publishing. This is how we get our data and our conclusions from that data out. We can't publish opinions without data to back it up. And that's because of the peer review. You can't say, well, I collected 10 things in 3 months and this is what I found, so therefore X is Y. Your reviewers are going to say, you didn't study it long enough, 3 months is nothing, you only have 10 samples, we're not going to publish it. And you're the only one saying that. Nobody's ever going to listen to it, nobody's ever going to see it. So to get published, you have to have a good sample size, you have to have done your study long enough, and you have to, your paper will be sent to the top people, in this case, top bear biologists, and they will chop it up. In fact, prepare yourself. Probably the highest journal in my business was the Journal of Wildlife Management. So when I was in junior high, I would always ask the girl that I really wanted to dance with first. And when she turned me down, I would go to the next girl I really wanted to dance with next. I learned how to accept rejection. It happened a lot. And publishing is kind of the same thing. So I sent it to the journal I really wanted to get it published in, the prettiest journal. and they rejected me. And you guys can't read it from this public, but they here say that my research potentially has merit. They gave me good reviews, but they were concerned that this was a catastrophic fire, which it was. They were concerned that I only had data from one fire, which is all I did. And so they state, although my manuscript contains some important results, unfortunately was rejected for publication in this journal. That's kind of common. Getting published because of the peer review process is difficult. We are extremely critical of each other, scientists are. We should be, because that's the only really way to find the truth. So I tried again. I would go to the next girl in the dance to ask her, and so I went to the next journal that I really wanted to get published in, and I made the corrections that the reviewers pointed out in my first draft, which improved it. I sent it to this journal, and Dr. Krausman, who was the editor at the time, sent it to, he reviewed it, and two other people who were anonymous reviewed it. Both agree that you have an outstanding data set, but it needs some improvement. Basically, here exact words, because I would like to see these data published. In my opinion, they would be a solid contribution to the literature. I invite you to consider all the comments and prepare a revision. So they didn't reject it, but they didn't accept it. I had to go through these comments, and they're not always nice. Sometimes people can get downright mean. I didn't have that as often as some of my other friends, peers did. But whereas this research has the potential to make an important contribution, I believe more work needs to be done to realize this potential. Basically, they're going to tell me, you didn't use the right statistics. You're making some assumptions based on your data that you collected that we don't agree with, or you need to give me some more data or literature to convince me, for example, that males ate the cubs. How do you know males ate the cubs? Did you find the cubs? Did you have collars on the cubs? No, I didn't. I made an assumption. Where did the how do you know? So I have to go back and try and make a case based on the data I collected. I mean, how do I know the cubs didn't starve? That was one of the comments made by the reviewers. So it was on this page. How do you know the cubs, just wasn't enough food for the cubs they starved, and how do you know the males ate them? How do you know the increased density affected them? You didn't find dead cubs. You don't have proof of that. Well, I went back and said, look, if the females are gaining 100 pounds every summer and they're in good enough condition to have cubs, then I don't think there's a lack of food, and the cubs didn't starve. I get to argue my case with these reviewers, and they accepted it. I made a logical, data-driven argument, and they accepted it. Every edit I've had, every time someone has negatively commented on my paper, it improves it. It does take some maturity to finally get to that level. The first time you try and publish, say in your late 20s, and you get rejected, it's pretty heart-wrenching because you've put 4 years into the study and you think it's your life and you're almost God and you think you're great, and you get over that pretty quickly. So this is what a peer review is. So when you see somebody on the news and a guy comes and he says, well, this data isn't peer reviewed, we're not sure it's correct. There's a reason for that. And that peer review means we haven't had a bunch of scientists look at this. This is only one person, and we want people to review it, and then we'll let you publish it, and then maybe it should make it into the news, or then it should be part of a conservation decision, but not before. Nobody's going to look at a website and say that anybody could write anything, blame anything on anything. That's not how science works. It has to be reviewed by other scientists. And but going back to arguing a lot. And in ecology and in the environment and the things that we're going to talk about in this class, I'm going to say things, but they're not always going to be 100% accurate. Chemistry and physics have laws. So if you do things at a certain temperature or you do things with a certain amount of force, the same thing is always going to happen. We're going to talk more about this, but that doesn't happen in nature. There are so many other variables. How much rain was there? What's the soil? How are you comparing this to that? And this is a great example that I used to show my students in wildlife at Arizona State University. So this is a table, and we're going to talk about predator-prey relationships later in the semester. But this report of predation is a limiting or regulating influences on ungulate population, so deer, elk, pronghorn, all these. And so here is an extensive table that has 21 examples where wolves, coyotes, mountain lions actually controlled or reduced a population. So predators in these 21 studies are affecting the prey population. So predators have an effect on prey. But wait a minute. Same chapter in the book. Second table. Studies where predators have been found not to control or limit the size of ungulate populations in North America. 22 studies. The exact opposite. So a lot of the what a mature scientist and I'm going to give you this opinion. You need to be skeptical of anything you hear. I would love to say I taught you how to think instead of what to think. I want you to look at things more critically. Hopefully I'll be helping you do that through the semester and giving you the background in ecology so you can look at things more critically. But because what happens in one place, a fire in Arizona may not affect bears the same way as it does in Montana. And I would be the first to agree with that. That's actually one of the comments one of the reviewers made in my peer review. And that's why one study we don't run off and say, okay, we got the answer, let's send the man to space. It took a lot of studies, it took a lot of argument, it took a lot of competing results to get things done. And that's what peer review means. Peer review means a critical analysis of some work that's been done, and then it goes into the literature, but no one jumps and runs and makes a bunch of decisions, or at least they shouldn't, based on one study. You need repetition. You need lots of studies. And that's kind of what they're talking about now on the whole blood plasma thing. One study found it worked, another study found it didn't work. Why are we forcing people to do it? I don't want to get into the pandemic because I'm not an epidemiologist and I don't want to be an expert. But what I'd like to get you guys to the point is, okay, we're only going to listen to peer-reviewed stuff. Just because it's on a website doesn't mean I have to believe it. Just because a journalist says it doesn't mean I have to believe it. You can certainly get different opinions from MSNBC and Fox News. That shouldn't or can't happen in science because of the peer review process. A reporter can't say anything without getting reviewed before they can go on the air, but they don't. So a reporter can say anything. Sometimes you get way different slants on the same item. Science does everything it can through the peer review process, and here's an example of someone trying to get published and getting all chopped up and told the work's not good enough, go back and redo it, and then it gets published. And hopefully that keeps us on the line for truth. So hopefully this gives you a better idea of what they mean by peer review, a little bit about bear biology and fire ecology in Arizona, and I will see you soon.